So, we will continue with our discussion on problem solving. We have already solved one problem which includes normal modes. Now, let us look at what problems we have in hand. Okay. So, linear triatomic molecule is something that we have already settled. Now, there is a problem number 5 which discusses this system actually. So, 3 masses or 3 beads actually connected by rings which are on this moving on this circular loop, and their angular displacements are theta 1, theta 2 and theta 3 respectively. Now, we have to take all the masses to be equal to m and all the all the spring constant to be equal to a, and we have to take the angular displacement as the generalized coordinate. We have to write down first the expression of kinetic energy and potential energy, then normal frequencies, orthogonal amplitude vectors, and we have to finally comment on the nature of the motion for different normal mode oscillations. Okay. So, let us look at this picture once again. We have a spring mass system which is on this rim. Okay. So, we have they are evenly spaced. So, one here and one here. These are beads actually of equal mass m and m, and they are connected by springs of equal spring constant. Okay. So, what I will do is I will mark them so that it is easy for you to see. So, these are the beads we are talking about. Let us say the radius of this is capital R. If this is the case, and the deviation let us say from equilibrium position, which was supposedly somewhere here, let us say theta 1, similarly for this one it will be theta 2, the third one will be theta 3 and like this. Now, and the spring constants are k, k and k. Now, for springs we do not care whether it is we do not discuss the spring kinetic energy or potential energy in terms of angular displacement, but in terms of linear displacement. But linear displacement and angular displacement, let us say if the linear displacement is x1 corresponding to this one, it will be simply r theta 1, similarly x2 will be r theta 2 and x3 will be r theta 3. So, for this spring let us say it is let us say 1, 2 and 3. So, the spring that connects 1 and 3, for that the kinetic energy potential energy expression will be half k x3 minus x1 square, which will translate to half k r square theta 3 minus theta 1 square, right. So, similarly we can write for the similar expressions for 2 other springs. So, what we are doing? We are looking at the compression of the spring, but what we are doing is using these relations in order to change this compression into angular displacements. So, we are basically writing this compression of a spring or expansion of a spring which in terms of the angular displacements. Now, if we do that, the total kinetic energy V will be half k r square theta 3 minus theta 1 square. Similarly, for this 2 it will be theta 1 minus theta 2 square, and for this 2 it will be theta 2 minus theta 3 square. So, I hope I could convince you that this is the right way of writing this potential energy. Now, if we open the brackets, it will be 2 theta 1 square plus 2 theta 2 square plus 2 theta 3 square, right, because for example, this one and this one will contribute 2 theta 1 squares, this one and this one will contribute 2 theta 2 square, it's like this. So, we have 2 of both theta 1 square, theta 2 square and theta 3 square, and then we have minus 2 theta 1 theta 3 minus 2 theta 1 theta 2 minus 2 theta 2 theta 3. Okay. So, I think we have written the matrix, I mean that entire expression nicely. Now, it is time to convert it to the matrix. So, B will be given by, see there is a factor of k r square which will be there, okay, and the matrix form I will just two along the diagonal, because both all the diagonal elements has a weight of 2. Now, for this term, let us say theta 1, or let us say first start with this term theta 1 theta 2, again we have to break it in a symmetric manner. So, 2 theta 1 theta 2 will be 2 theta 1 theta 2, so sorry 2 theta 1 theta 2 will be theta 1 theta 2 plus theta 2 theta 1, so that the matrix remains symmetric. So, it will be minus 1 here and minus 1 here and minus 1 here, minus 1 here, minus 1 here and minus 1 here. Okay. So, it is a matrix where we have diagonals as 2 and off diagonals as minus 1, all of it. I think you have, I could make you understand why it is like this. If not, please try to look into this functional form of V, that is very important. How to get the V and what is the functional form, and try to correlate this two. Okay. Next, okay, so this is your potential energy. Let us write it for kinetic energy. Oh, sorry, I should not have removed it anyway. So, sooner or later you have to do it. Now, kinetic energy is pretty straightforward, because T will be half m x1 dot square plus x2 dot square plus x3 dot square. It will be half m r square theta 1 dot square plus theta 2 dot square plus theta 3 dot square, right. So, once again we can write this A matrix as, okay. So, there will be an m r square term outside, m r square term outside, and it will be simply 1, 1 and 1, that is it. Okay. So, now we have to find out the normal mode frequencies. So, we have done our first bit. We could write the kinetic energies and potential energies in terms of these two matrices. Now, it is time for us to find out the normal frequencies of oscillation. Now, in order to do that, we have to solve this determinant, which was determinant of B minus A p square equal to 0. By the way, if you like, you can write omega also in place of p, because in many books, many textbooks, people have used omega as a standard notation for p. I am using it because it is in the very nice textbook of Professor Roy Choudhury on notes on classical mechanics. So, I am following this convention. It's just for my convention, it's you do not have to follow this. Okay. Now, it will be r square outside, okay, b minus ar, right. So, it will be 2k minus m p square minus k minus k minus k 2k minus m p square minus k minus k minus k 2k minus m p square equal to 0. Best thing would be to get rid of this r square anyway, because this is not contributing anyway. It is a common factor between these two matrices, so it will cancel out. Now, if we open up this bracket, okay, it is a little longer calculation, but it is extremely doable, nothing wrong with it. I will show you maybe 1 or 2 steps and write the final answer, because this is something that you can try yourself once you know the final answer. So, So, if we just open up this determinant, I am pretty sure you know how to do it, all of you, you know how to open up a determinant. So, if we do that, it will be 2k minus mp square outside, and inside bracket we will have 2k minus mp square whole square minus k square minus k square, and we have second term which is minus k. So, we have to do this minus this. So, k square minus k square plus k square plus k times 2k minus mp square, right, and there will be a third term which will be again minus k, and it will be k square plus k times 2k minus mp square. Now, you see that these two terms are identical. So, what we can do is we can simply add them together, put a 2 here. So, it will be 2k, and that is it, we are good, and this is equal to 0. That is the equation. Now, if we have to open it up further. If we do that, okay, just give me a second. Yeah, right. So, if we do that, that is the pain with small oscillation problems. We have to solve this complicated algebraic equations. I mean, these are fun sometime, but sometime it is just that answer will be something very simple, but still I have to go through that long steps. But what can you do? This is life. Okay. There was some simplification I did. Right. Oh, okay. So, what I did was I opened this one inside before doing anything here. I opened this one inside. So, it will be 2. So, it will be 2k square if I do that, and there will be a k here. Now, 2k square will be adding to this. So, it will give you 3k square, and 3k will put a k square here minus mp square, 3k minus. Okay. So, this was one simplification I did beforehand, and anything else? No, and now you have to open up the bracket. So, if you do that, oh yeah, also this one. So, it will be oh, okay. So, this I wrote as 2k minus mp square. So, a square minus b square. So, this will be a plus b into 2k minus mp square minus k, right, minus 2k square into 3k minus mp square equal to 0. Okay. So, again we will see that this term will be nothing but 3k minus mp square, right, 3k minus mp square, and this will be k minus mp square. Right. Now, we can, so this is already factorized, this term, and there is and we see that 3k minus mp square is the common factor, 3k minus mp square, that is the common factor. If you take that common from both the terms, what is left is this multiplied by this, which will be 2k square minus m p 2 m p square k minus k m p square, right, square plus m p square whole to the power 4 minus 2k square equal to 0. Okay. I think now it looks more or less nicer, right, and m p square k. So, finally, you see these two terms are actually 2 times, I mean 2 m p square k and m p square k. So, this will give you 3 k m p square, and it will be m p square, sorry, m p square whole square, not to the power 4 whole square minus 3 m k p square, right, equal to 0. Now, what we can do is we can take p square out of this term. So, we can totally factorize it in the following form. So, we can write p square 3 k minus m p square, and it will be m square. So, yeah, m can also be taken out. So, it will be m. So, it will be p to the power 4 p square we have taken out, m p square minus 3 k, just like this, yeah. So, these two terms are taken out, and you see these two terms will give you same root. So, the roots will be p equal to p 1 equal to 0, p 2 equal to p 3 equal to it will be 3 k by m. So, these are the eigenfrequencies of the system. Okay. So, it was not that big as we have thought initially it will be. Of course, there are some small algebraic manipulation, but this is nothing difficult. Okay. So, we have the eigenfrequencies of oscillations. So, we have one 0 frequency and other distinct frequency, so there is basically one frequency which corresponds to vibration of the system, and there is a 0 frequency. Now, 0 frequency, if we try to now calculate the amplitudes of each of the terms, if we try to calculate the amplitude, okay. So, for p 1 equal to 0, it will be a straightforward calculation. We once again have to use this equation, but not in the determinant form, we have to use it in the matrix form. So, if we do that, b minus a p square, so p is equal to 0, so it will be simply b. Okay. So, this b matrix will be 2 minus 1 minus 1 minus 1 2 minus 1 minus 1 minus 1 2, and we have a 1 1 a a 2 1 a 3 1 equal to 0 0 0. And if you write out 3 equations and solve it, you do not have to even solve it really. If you look at it carefully, you will realize it gives a solution that a 1 1 equal to a 2 1 equal to a 3 1, which is equal to 0. Which is equal to some x. And if we now use our normalization algorithm, which is a L a k equal to delta L k, if we do that, so we have x square 1 1 1 m m m, which is also 1 1 1 essentially. So, basically I can write this as 1 1 1, we multiply this by m, and 1 1 1 equal to 1. If we do that, what do we get? We get x equal to 1 by root 3 m. You can do it yourself. Okay. So, sorry, it is not visible in this part, just shorten it a bit. So, it will be 1 1 1 1 1 1 0 here 0 here and 1 1 1 equal to 1. So, this equation will translate to this. Now, if we do that, we have x is equal to 1 by root 3 m. So, our solution for A1, I will just write it here. Okay. A1 is 1 by root 3 m 1 1 1. Fine. Now, for if we put P2 equal to P3 equal to root 3 k by m, if we do that, just take P2 equal to root 3 k by m. So, AP square, P square or rather MP square, MP square will be P square, yeah, it will be 3 k. Okay. So, if you put 3 k here in this equation, or rather in this equation multiplied by the matrix form. So, you have 2 k minus 3 k minus k minus k minus k 2 k minus 3 k minus k minus k minus k 2 k minus 3 k. Very good. And we have a 2 1, a 2 2 or sorry, it will be a 1 2 1 2 2 2 3, right. Right. I always mix up between which one should I use, 1 2 2 2 3 2. You have to use, it will be 1 2 2 2 3 2, right. Right or wrong? Just let me think. So, Q1 will be 1 C1, no, it will be 1 2. Yeah, so C2 2, so 1 2 2 2 3 2, yeah, this will be the one, yeah, which will be equal to 0 0 0. Sorry, I am always mixing up this indices. So, we have to better if we remember q k is equal to sum over L a k L C L e to the power I P L T plus theta L. If we remember this relation by heart, it will solve the problem. See, for when we write the general solution, Q1 will have A 1 1, right, A 1 1 C 1 e to the power I P 1 t plus A 1 2. So, this has to be A 1 2 and third one will be A 1 3. Okay. Right. Now, see this actually these are all minus k's. So, we have a minus k here, minus k here and minus k here. So, these are essentially collection of 3 equations. All 3 equations will give you 1 2 plus A 2 2 plus A 3 2 equal to 0. Now, this is a non-trivial case, because as in we can choose many combinations, right. We can choose n number of combinations. We can choose A 2 2 equal to 20, A 1 2 equal to 0, A 3 2 equal to minus 20, that is one possibility. Similarly, we can choose this to be 25, this to be minus 5, this to be minus 20, that is also another possibility. But the catch is, if you go back to the problem, we have to find out the set of normalized and orthogonal eigenvectors. Normalization is something that we can very easily do once we get rid of, we have to put this factor in front. So, that is not the problem at all. Catch is, we have to find out orthogonal sets of eigenvectors. We already have one vector. We have to find out 2 other vectors which are orthogonal to this one. okay, and also mutually orthogonal between each other. So, the choices are not many. So, we can choose one combination, for example, to be y and minus y and 0. This is one combination. This is definitely orthogonal, because basically we can within a normalization factor we can write this as 1 0 minus 1, right. So, if we write 1 0 minus 1, we will get so if we write a 2 equal to some factor y 1 0 minus 1, and if you compute a 1 dot a 2, or rather a 1 transpose a 2, it will be, forget about the factors, there will be some factors in front, it will be 1 1 1 1 0 minus 1, right. So, if you do that, it will be 1 minus 1 equal to 0, and this is the normalization condition, or this is the orthogonality condition, not normalization, that a L A or a L dagger A M is equal to delta L M. This is the condition for orthogonality, and we have to follow this. Now, so I have not explicitly mentioned this, I do not think I have explicitly mentioned this condition well when we were discussing the theory, but generally when we are talking about eigenvectors in general, even for rigid dynamics also we have, I think we have discussed it in a little bit. Whenever we are finding out eigenvectors, it is important that we find out a set of orthogonal eigenvectors. In some cases, it is not possible to find out orthogonal eigenvectors, but at least we can, we can try our best. So, right now whatever we have, we can choose two, we have to make two choices which are at least linearly independent. I mean, these are all linearly independent by the construction of the problem, all these vectors are linearly independent. Even if we do not find orthogonal condition, orthogonal eigenvectors at the beginning, we can use something called Gram-Schmidt orthogonalization, which you will learn probably in your mathematical physics lectures, or you have already known it. Using that, we can construct a set of orthogonal eigenvectors. But right now, we do not have to do that much. We have chosen, let us say, this one. Other combination will be this. So, we can choose a 3 equal to some factor z 1 minus 2 1. Check between these two if they are orthogonal, check between these two if they are orthogonal. Okay. It will be, I mean, by the construction I am giving you the answer, but this is how we choose it. Now, for normalization, the normalization factor of this will be 1 by root 2 m, whereas for this it will be 1 by root 4 m. So, we have, sorry, it is not visible, I will 3 equal to 1 by root 4 m vector 1 by root 2 m vector and this vector. So, these are the 3 normalized eigenvectors. Now, we are closing in order to finish this problem. So, the general solution following this construction can be written as theta 1, theta 2, theta 3. I am just writing a matrix equation which will include 3 linear equations C 1. Okay, so, there will be a factor coming due to normalization equal to C 1 by root 3 m 1 1 1, right. Oh, by the way, these two eigenvectors are although so why we had trouble in order to find two mutually perpendicular orthogonal eigenvectors, because the eigenvalues are degenerate. So, we had to choose. Okay. So, and this is 0 frequency. So, we do not have any amplitude or phase term. 2m 1 0 minus 1 e to the power I p this is root 3k by m plus phi 1, sorry t will be here, and we have C3 by root 4m 1 minus 2 1 e to the power I root 3k by m t plus phi 2. Yeah, great. So, this is the total solution of the problem. Of course, theta 1, C1, C2 and C3, phi 1 and actually I should write phi 2 and phi 3. Yeah, because just to keep it consistent. So, we have 5 conditions and we need at least 5 initial conditions, 5 unknowns. So, we need at least 5 initial conditions to order to get a full description of it. But let us consider, and at the end let us consider what are these normal modes telling us. The first normal mode with the frequency 0, it is actually a pure rotation, and see that amplitudes are equal. So, when all these are moving in one particular direction, with uniform angular velocity, that is the situation given by p 1 equal to 0, p or rather frequency equal to 0. So, you see amplitudes are equal and it has to be a pure rotation. Second and third describes the same frequency mode, but with different sets of amplitude. In one, so this is for 1, okay, we don't need all these ornaments we don't need anymore. Okay. Now, for this one, see 1 is going this way. This is 1, 2 and 3. 2 is stationary, 3 is going the other way by equal amplitude. So, in this mode, one of the masses, so it's not distinguishable whether we choose this one or which one is the first mass, we cannot say, but all we can say that in this particular normal mode, out of 3 masses, one of the mass is stationary and 2 other masses are going like this or coming back like this. So, they are executing a oscillation around its equilibrium position, keeping the second mass constant. And if you now calculate the what you call the center of mass for this system, see at equilibrium the center of mass will be at the center, right. If you take origin at here, the center of mass will be at the center. Now, I will just leave it to as an exercise to show that the center of mass is not changing in this oscillation. Similarly, for the third oscillation, what happens is the first one and the third one, they are moving in the same direction. So, if it is moving like this, this one is moving like this, and the second one is moving in an opposite direction with double the amplitude. So, if this one is like this one is going like this one is going like that. So, this one at the same time will go double the amplitude in the opposite direction, once again keeping the center of mass at the fixed position at the center. Okay. So, I will just leave that to you as an exercise. So, this is a very good example and why I chose this problem to begin with, because if you look at the matrix, the B matrix especially, here all these are connected, right. So, we have a connection between first and the third frequency, first and the third mass through this matrix. Similarly, we have a connection between second and third. So, it is a matrix where every it is a potential energy problem where every movement affecting every possible potentials, or rather I would say this one, the movement of this one also influences the potential energy of this particular spring, although they are not directly connected. And also it gives you a very interesting concept of finding orthonormal eigenvectors, orthogonal and normalized eigenvectors in a degenerate case. Okay, so that is why I chose this problem. We have 2 more problems and we have 1 more lecture in hand in order to finish this course. So, right now we have to close this lecture. Thank you.